Hello friends, welcome to another interesting video in electromagnetics and antennas series. In this video we'll continue our discussion of finding electric field E due to surface charge density. In the previous video we found the electric field E due to the line charge density. So if this is something that interests you, then please keep watching. Before we can start the discussion of finding the exact value of E, we need to have some key points in hand. The first one is that it's an extension of E due to line charge density. So we know the electric field intensity due to a line, and if we integrate numerous lines or infinite lines, so that will make up a surface, and that will be the electric field intensity due to surface charge density. So it's an extension of E due to line charge density. And we must also remember the formula for E for line charge density, which was rho L upon 2 pi epsilon naught R, and it was in the radial direction. If you have any doubts regarding this formula, you can refer to the previous video. That is highly recommended. So let's consider some surface charge density spread over the YZ plane. So here we have the YZ plane with the surface charge density rho S, and this plane is extending from minus infinity to infinity for Y and minus infinity to infinity for Z as well. On the surface, I take up a line or negligible width dy, and it is at a distance y from the origin, and we take up a point A at x-axis. So we'll try to find our electric field here. So let's consider some geometry here. The distance of A from this strip with the width dy is this capital R, and this capital R is x square plus y square under root. And let's say if this makes an angle theta here, so this angle will also be theta, and cos of theta will become x upon x square plus y square. Now, why is this geometry important to understand? We'll see in a minute. So next important thing is that the total force or the electric field intensity felt will be exactly normal to this point, because all the other components, they are going to be cancelled. For example, if we consider a strip of wire here, it'll exert some force which will be cancelled with this one. So all the other components in x and y directions, they are going to be cancelled with each other. So this is from geometry, cos of theta x upon x square plus y square, and this is from the previous discussion that dE is going to be rho s dy upon 2 pi epsilon naught, and this is r. This is our r distance, which is here, and multiplied by cos of theta. Now this is the rationale. I've written it here also. R is x square plus y square, and rho L, the relation between the line charge density and the surface charge density, is simple, rho s dy. As I mentioned, this crucial point that all components of y and z directions will be cancelled when we integrate the strip from minus infinity to infinity for y and minus infinity to infinity for z. So only force that acts will remain in the normal direction, which is in this case is x. So had we considered our surface charge density to be in, let us say, YZ plane, then it would be in the y direction, so so on and so forth. So the force or the field, electric field, which we're talking about, will only exert in the normal direction. And next is simple mathematics. If we integrate this dE, we get the total electric field which we are striving to find out, and inside we have rho s dy upon 2 pi epsilon naught, and cos theta, this is the expression for cos theta. Of course, cos theta is x upon x square plus y square under root, these two under roots x square plus y squares, they've combined to become 1. So I've taken out rho s upon 2 pi epsilon naught outside, and then I have this integration from minus infinity to infinity, x upon x square plus y square dy, which gives me tan inverse y by x, and the limits are minus infinity to infinity. So simple mathematics here, putting the values of infinity and minus infinity gives me pi by 2 minus of minus pi by 2. So this gives me pi, this pi will get cancelled with this one, so I get my total electric field to be equivalent to rho s upon 2 epsilon naught, and in this particular case it will be in the direction of x. So that's noteworthy. And finally, if we get some question like that I have an xy plane where some charge density rho s is 1 nanocoulomb per meter square, then if we were to find the total electric field intensity, that will be simply rho s, which is 1 nanocoulomb upon 2 into epsilon naught. So it has got nothing to do with the distance or anything else. So this formula has become even more simpler than the formula for the line charge density. So knowing the electric field E for line charge density will greatly help you to find the electric field due to surface charge density. And that's about it for today's tutorial. That's what I wanted to discuss. In the next video, I'll talk about electric field E due to volume charge density, and that will conclude our discussion for finding electric fields. And if you liked the video, give it a thumbs up, consider subscribing to the channel, and share this video amongst your friends. I'll see you around in the next week, and take care, stay safe, stay at home, and take good care of your health.